the quantum Zeno effect is a situation in which an unstable particle, if observed continuously, will never decay. One can freeze the evolution of the system by measuring it frequently enough in its known initial state. The meaning of the term has since expanded, leading to a more technical definition in which time evolution can be suppressed not only by measurement. The quantum Zeno effect is the suppression of unitary time evolution caused by quantum coherence in quantum systems provided by a variety of sources: measurement, interactions with the environment, stochastic fields, and so on. As an outgrowth of study of the quantum Zeno effect, it has become clear that applying a series of sufficiently strong and fast pulses with appropriate symmetry can also decouple a system from its cohering environment. The name comes from Zeno's arrow paradox, which states that because an arrow in flight is not seen to move during any single instant, it cannot possibly be moving at all. The comparison with Zeno's paradox is due to a 1977 paper by George Sudarshan and Baidyanath Misra. The first rigorous and general derivation of this effect was presented in 1974 by De Gasperis ALll. It had previously been described by Alan Turing in 1954, resulting in the earlier name Turing paradox. The idea is contained in the early work by John von Neumann, sometimes called the reduction postulate. It was shown that the quantum Zeno effect of a single system is equivalent to the indetermination of the quantum state of a single system. According to the reduction postulate, each measurement causes the wave function to collapse to a pure eigenstate of the measurement basis. In the context of this effect, an observation can simply be the absorption of a particle, without an observer in any conventional sense. However, there is controversy over the interpretation of the effect, sometimes referred to as the measurement problem in traversing the interface between microscopic and macroscopic. Another crucial problem related to the effect is strictly connected to the time-energy indeterminacy relation. If one wants to make the measurement process more and more frequent, one has to correspondingly decrease the time duration of the measurement itself. But the request that the measurement last only a very short time implies that the energy spread of the state on which reduction occurs becomes increasingly large. However, the deviations from the exponential decay law for small times is crucially related to the inverse of the energy spread, so that the region in which the deviations are appreciable shrinks when one makes the measurement process duration shorter and shorter. An explicit evaluation of these two competing requests shows that it is inappropriate, without taking into account this basic fact, to deal with the actual occurrence and emergence of Zeno's effect. Closely related is the watchdog effect, in which the time evolution of a system is affected by its continuous coupling to the environment. Description: unstable quantum systems are predicted to exhibit a short time deviation from the exponential decay law. This universal phenomenon has led to the prediction that frequent measurements during this non-exponential period could inhibit decay of the system, one form of the quantum Zeno effect. Subsequently, it was predicted that an enhancement of decay due to frequent measurements could be observed under somewhat more general conditions, leading to the so-called anti-Zeno effect. In quantum mechanics, the interaction mentioned is called measurement, because its result can be interpreted in terms of classical mechanics. Frequent measurement prohibits the transition. It can be a transition of a particle from one half-space to another, as in the time of arrival problem, a transition of a photon in a waveguide from one mode to another, and it can be a transition of an atom from one quantum state to another. It can be a transition from the subspace without coherent loss of a qubit to a state with a qubit lost in a quantum computer. In this sense, for the qubit correction, it is sufficient to determine whether that coherence has already occurred or not. All these can be considered as applications of the Zeno effect. By its nature, the effect appears only in systems with distinguishable quantum states, and hence is inapplicable to classical phenomena and macroscopic bodies. Various realizations and general definition: the treatment of the Zeno effect as a paradox is not limited to the processes of quantum decay. In general, the term Zeno effect is applied to various transitions, and sometimes these transitions may be very different from a mere decay. One realization refers to the observation of an object as it leaves some region of space. In the 20th century, the trapping of a particle in some region by its observation outside the region was considered as nonsensical, indicating some non-completeness of quantum mechanics. Even as late as 2001, confinement by absorption was considered as a paradox. Later, similar effects of the suppression of Raman scattering was considered an expected effect, not a paradox at all. The absorption of a photon at some wavelength, the release of a photon, or even the relaxation of a particle as it enters some region, are all processes that can be interpreted as measurement. Such a measurement suppresses the transition, and is called the Zeno effect in the scientific literature. In order to cover all of these phenomena, the Zeno effect can be defined as a class of phenomena in which some transition is suppressed by an interaction one that allows the interpretation of the resulting state in the terms transition did not yet happen and transition has already occurred, or the proposition that the evolution of a quantum system is halted if the state of the system is continuously measured by a macroscopic device to check whether the system is still in its initial state. Periodic measurement of a quantum system. Consider a system in a state A, which is the eigenstate of some measurement operator. Say the system under free time evolution will decay with a certain probability into state B. If measurements are made periodically, with some finite interval between each one, at each measurement, the wave function collapses to an eigenstate of the measurement operator. Between the measurements, the system evolves away from this eigenstate into a superposition state of the states A and B. When the superposition state is measured, it will again collapse either back into state A as in the first measurement, or away into state B. However, its probability of collapsing into state B, after a very short amount of time t, is proportional to τ squared, since probabilities are proportional to squared amplitudes, and amplitudes behave linearly. Thus, in the limit of a large number of short intervals, with a measurement at the end of every interval, the probability of making the transition to B goes to zero. According to coherence theory, the collapse of the wave function is not a discrete, instantaneous event. A measurement is equivalent to strongly coupling the quantum system to the noisy thermal environment for a brief period of time, and continuous strong coupling is equivalent to frequent measurement. The time it takes for the wave function to collapse is related to the coherence time of the system when coupled to the environment. The stronger the coupling is, and the shorter that coherence time, the faster it will collapse. So in that coherence picture, a perfect implementation of the quantum Zeno effect corresponds to the limit where a quantum system is continuously coupled to the environment, and where that coupling is infinitely strong, and where the environment is an infinitely large source of thermal randomness. Experiments and discussion. Experimentally, strong suppression of the evolution of a quantum system due to environmental coupling has been observed in a number of microscopic systems. In 1989, David J. Wineland and his group at NIST observed the quantum Zeno effect for a two-level atomic system that was interrogated during its evolution. Approximately 5009B+ ions were stored in a cylindrical penning trap and laser-cooled to below 250 mK. A resonant RF pulse was applied which, if applied alone, would cause the entire ground state population to migrate into an excited state. After the pulse was applied, the ions were monitored for photons emitted due to relaxation. The ion trap was then regularly measured by applying a sequence of ultraviolet pulses, during the RF pulse. As expected, the ultraviolet pulses suppressed the evolution of the system into the excited state. The results were in good agreement with theoretical models. A recent review describes subsequent work in this area. In 2001, Mark G. Raison and his group at the University of Texas at Austin, observed the quantum Zeno effect for an unstable quantum system, as originally proposed by Sudarshan and Misra. They also observed an anti-Zeno effect. Ultra-cold sodium atoms were trapped in an accelerating optical lattice and the loss due to tunneling was measured. The evolution was interrupted by reducing the acceleration, thereby stopping quantum tunneling. The group observed suppression or enhancement of the decay rate, depending on the regime of measurement. The quantum Zeno effect is used in commercial atomic magnetometers and naturally by Bird's magnetic compass sensory mechanism. It is still an open question how closely one can approach the limit of an infinite number of interrogations due to the Heisenberg uncertainty involved in shorter measurement times. It has been shown, however, that measurements performed at a finite frequency can yield arbitrarily strong Zeno effects. In 2006, Stride et al. At MIT observed the dependence of the Zeno effect on measurement pulse characteristics. The interpretation of experiments in terms of the Zeno effect helps describe the origin of a phenomenon. Nevertheless, such an interpretation does not bring any principally new features not described with the Schrödinger-Dingo equation of the quantum system. Even more, the detailed description of experiments with the Zeno effect, especially at the limit of high frequency of measurements, usually do not behave as expected for an idealized measurement. It should be noted that the quantum Zeno effect is dependent upon the reductionist postulate for reconciling the measurement problem. Thus, the quantum Zeno effect does not apply to all interpretations of quantum theory. In particular, the many-worlds interpretation and the quantum logic interpretation. Also, the quantum Zeno effect may only hold for directly observed quantum systems, meaning that statistically observed systems might not be affected by the Zeno effect. These qualifications mean that the Zeno effect may possibly be a useful experimental design for testing the many-worlds hypothesis, the quantum logic hypothesis, and various hypotheses related to quantum computing and require analysis of the mechanism of the interaction. It was shown that the quantum Zeno effect persists in the many-worlds and relative states interpretations of quantum mechanics. See also: external links. Zeno QCL, a computer program written in QCL which demonstrates the quantum Zeno effect, quantum Zeno effect on arXiv.org. Notes. References.